team representing Iolani School in Honolulu, Hawaii. I'm Kimberly Peterson.
Hi, I'm Arnold Chen. I'm Evan Long.
Hi, I'm Courtney Otani.
Hi, and I'm Deanne Ugawa. Our research topic is on wave energy. To address our research purpose, we developed two distinct wave energy conversion devices and tested their efficiencies, feasibility, and applicability in marine environments.
As you can see from this pie chart, fossil fuels are currently the most consumed energy source. In 2010, 80.6% of world energy consumption was from fossil fuels, with only a measly 16.7% coming from renewable energy sources such as wave power. So the main three fossil fuels are coal, petroleum, and natural gas. Fossil fuels are considered non-renewable resources because they take millions and millions of years to form. Therefore, fossil fuels will become more scarce as we continue to use vast amounts of them.
As fossil fuels become more scarce, energy prices will rise. Because fossil fuel prices have continued to rise, more emphasis has been placed on renewable energy resources. And in Hawaii alone, we utilize geothermal energy, which is in use on the Big Island of Hawaii, solar power, and wind energy. However, a new frontier of renewable energy has arrived: wave energy.
Wave energy actually derives its power from wind energy, which in turn derives its power from the uneven heating of the Earth. The uneven heating of the Earth creates temperature gradients across the Earth, which in turn makes areas of denser air and light, hotter air. The light, hotter air tends to float upwards, and in its place comes the cold, denser air, which makes what we call wind.
The size and strength of the waves depend on three factors: the size and duration of the wave and the distance traversed. A longer, faster wind produces a more energetic wave. Also, the farther a wave travels without dying off, the more energetic it becomes.
Although by definition, a wave cannot be formed without the motion of water molecules, water itself only travels in a circular fashion. This is exhibited, for instance, in a buoy floating in the ocean. The buoy will only float up and down, never with the wave, until the wave breaks near the shoreline. And at that point, the waves do not move in simple harmonic motion. Okay, so to calculate the energy within a wave, we use this equation specifying the total amount of internal energy within a wave propagating fluid, such as seawater. We coupled this result with the powers, experimental powers of our wave energy converting devices to find their respective efficiencies. Okay, so the power of a wave per meter width equals rho, or density, times the gravity squared, times the height of the wave squared, or the amplitude, times the average time of the period, divided by 32 pi. Okay, to put some numbers out there, a 6-inch or 15-centimeter wave with a period of just about 20 seconds would have a power output of just under 500 watts per unit width of the wave. Although this is about potential energy, in reality, we can only harness a fraction of this amount because of non-conservative forces such as friction on the bearings, and due to the fact that we only address 1 out of the 6 degrees of freedom, which Kimberly will talk about next.
So the ocean contains 6 degrees of freedom, or in other words, the ocean can move in 6 ways. They are heave, sway, surge, pitch, yaw, and roll.
These are some of the various types of wave energy conversion devices that harness the 6 degrees of freedom. This is the oscillating wave surge converter, the point absorber, the overtopper, the oscillating water column, the bobber, and the attenuator.
The two specific wave energy conversion devices we focused on were the Savonius turbine and the heat energy converter.
Alright, so the purpose of our project was to test and compare two divergent or different wave energy conversion devices in terms of their efficiencies, feasibility, and applicability in marine environments such as in the ocean.
Okay, so we started our experiment by first doing our research. So we first went to Ocean IT, an innovative company which showcased the Savonius wave turbine. And we also went to the University of Hawaii at Manoa campus, where Dr. Michelle Tang and Mr. Richard Carter taught us about waves and the engineering of wave energy converting devices. We also listened to a presentation by Mr. Seki from the Hawaiian Electric Company, where he explained how wave energy is feasible as a substantial source of renewable energy.
We designed our wave turbine and our heat energy converter, and then along with that, we made a homemade wave tank out of wood and waterproof protective wrap. And then second, we built our wave turbine and our heat energy converter. We'll show you a movie of one of our tests. So as you can see in this movie, the turbine is spinning from the current produced by the sink, from the water coming from the sink.
We built two models of both of our wave energy conversion devices, one for the ocean testing, which were larger models, and another set for the UH wave tank. And then we went to the ocean to test for voltage and amps, and the waves there ranged from 15 centimeters to 45 centimeters. Then we went to the UH campus and tested the smaller wave energy conversion devices in their wave tank.
So the first wave energy conversion device that we used was the was the turbine, and that harnessed the pitch motion of the waves. The heat motion of the waves, which is the circular motion that the particles of the wave exhibit. And we'll show you a video in a moment, but the turbine only rotates in one direction, even if the water is coming either way, because if it comes this way, it catches the top one, and if it comes the other way, then it catches the bottom one. And the turbine was created using an axle, which was connected to a small motor using sprockets and chain. And the friction was a bigger factor in this device so we used a weaker motor to reduce the friction. And we put bearings in the wood holding the turbine's axle to further reduce the impact of friction and produce more electricity. So here's our video of our ocean test with our turbine. And when it starts up, then you can look at the chain and see the chain moving as the wave comes by, even if you can't see the actual turbine moving. That shows that the turbine was moving when the wave came by and it produced the electricity.
The second wave energy conversion device that we built was the vertical floating device that harnessed the up and down motion of the waves. We utilized a weighted styrofoam that was attached to a chain, which with sprockets also attached to the NXT motor to create our electricity. Because of the way that this device works, it outputs negative and positive voltage. So we created a diode bridge which would allow the voltage to be transferred to only positive, whether it was negative when it originally started moving the motor. Now we will show a video of this device being tested in the ocean. So as you can see, when the wave passes by, it's able to move the styrofoam up and down, which also moves the chain.
For the turbine wave energy conversion device, the peak voltage was 0.3 volts. The peak current was 0.55 amps, and the peak power, using the equation P equals I times V, the output was 0.0165 watts. Using the results from the wave power equation, we found that the turbine's efficiency was approximately 9 times 10 to the negative 4%. The irregular peaks that you see in the graphs are from the waves coming in intermittently.
Okay, for our vertical floater wave energy conversion device, we obtained a peak voltage of about 1.55 volts and a peak current of 0.1 amps, giving a peak power output given by the equation P equals IV, again, to be 0.155 watts. The efficiency was 8.8 times 10 to the negative 3%, which is around 10 times that of the turbine. However, as you can see, both efficiencies were really quite low, and that's because, as I said earlier, of non-conservative forces at play, such as friction on the bearings, and due to the fact that we only addressed 1 out of the 6 degrees of motion.
Okay, so the turbine is feasible on a larger scale. To maximize the power output, it should be in strong currents and with waves with long wavelengths. Also, it's bidirectional, so it only turns in one direction, no matter which way the wave turns, as my partner described before. So the best place to place these would be near shore or in strong, deep water currents, as can be found in the Bay of Fundy in Canada.
So our vertical floater is also feasible on a large scale, and it would be best in places where there's a high amplitude and frequency, and the waves could come in any direction because no matter what direction, the floater will still move up and down. And this device should be placed offshore of a breaking point because that would totally kill our device. And And places like these, for example, is the North Shore of Oahu.
In order to optimize our two devices, we need further experimentation and research. Larger devices results seem to be better because of the less friction that they have, and we also need optimal sites to test our wave energy conversion devices.
Okay, so for further research, we suggest reducing friction as much as possible and optimizing our designs. Wave energy is, of course, still in its early stages of development, so it needs time and energy, time to be developed.
There are many people we would like to thank for helping us along with our project, and these are just a few. And especially, we would like to thank our mentors, Dr. Mark Lindsay and Dr. Holly Lindsay, for always being there for us and helping us with our entire project.
And here's our bibliography. So if you want to learn more about wave energy conversion devices, you can use some of these resources.
Thank you for your time. Does anyone have any questions?